Okay, so we have our Cartesian axis here, and we have our vector here, and we know that we have an angle here, alpha, let's call it alpha, and this is x, y, and this is x. We know that these are the coordinates, x1, y1, and we know that this length here from the Pythagorean theorem is the length of the vector times sinus alpha, and the other is cosinus alpha. Now, to make my life easy, I will pick a very simple vector which has 1 and 1 as coordinate. So if you no 1 and 1 1 over square root of 2 1 over square root of 2 and 1 over square root of 2, of course. Yes, sorry about that, I was forgetting about the normalization constant. Let me rewrite it. I mean, it's an easy vector, but I'm sorry for the square root of 2, but it's not my fault. It's there for a reason. So this vector here, meaning that x1 and y1 has this particular length. What makes this special is that the length squared is 1 over square root squared plus 1 over square root squared. Okay, but this is 1 over 2 plus 1 over 2. This is 1, meaning that the length of the vector is 1 because the square root of 1 is 1. With pluses minus, but we pick the correct sinus because it's a positive length. So let's forget about L because L is equal to 1 in this case. And now we can see that what happens if we, let me erase this bit here to make it slightly larger. Okay, now we don't need it in the x direction, but in the y, yes. So I want to make a rotation of the vector. Okay, so now if we rotate it by some degree, which I'm not, but I want to put it here, for example. Okay. Oh, sorry about that. This is horrible. I want to place it exactly like here. Okay, vertical. So, and this is a rotation of the vector, meaning that the angle alpha has increased by that much. So it's another angle, alpha 1. In this case is 90 degree. And we know that this is a sinus, okay? And we know that the length is 1, so y1 is equal to 1, x1 is equal to 0. And if you remember, what's the angle alpha that we need to give to the sinus in order to get 1, which is 90 degree, is exactly pi over 2. So we know that with alpha equals pi over 2, which can be related to 90 degrees angle, we have the vector, vertical vector, that with the same length. The same length is still 1 because we just rotate the vector. And we can keep going doing this. We see that's why it's periodic, because if we rotate by other 90 degree, just a sec, I lost my pen. Yes. if you rotate by other 90°. Now, if you remember the graph, this is still 1. My drawing is not on scale, but this is 1, actually -1, and this is the other 3 point, not 3 point, alpha equals to 3/2 pi. No, pi, sorry, just pi. This is 180°, so it's pi. And then we rotate again by the same amount, always 90°, and we get, in this case is y -1, still -1, but it's y-axis, and then we go back to here, it's 1, and then we can complete the circle with this unknown angle that maybe, no, we know what it is. It's pi/4 in this case, because when the alpha is pi/4, which is 45 degrees, related to 45 degrees, we know that we are dealing with a square of diagonal, with a diagonal which is unit length. So this must be 45 degrees, and this is the reason why, okay? Because we know that the diagonal of a square is 45 degrees because it cuts the 90-degree angle in half. Okay, just to say that the sinus and cosinus are related easily by rotation, by the rotation of a vector. It's just rotation, so when you don't scale the length, because if you change the angle of the vector, so you assign it another number, you can literally move it along this circle, big circle, green circle, that is the trigonometric circumference that represents basically the 2D graph in the 2D space, the values of sinus and cosinus. Okay, so now where is the link with matrices that I want to do? I mean, there are many ways to, of course, introduce the concept of matrices, and I will not go very abstract. I will pick one that I need, and it's connected to the idea of rotation, because I want to use it later on for other slides with exponentiations and power series and qubits and things like that. So I will give an example of matrices which is well known, as I said, rotation in 2D plane, with real numbers. I will give you an idea of other kind of matrices that do simple operation on vectors, but of course there are tons of things that we can say about a matrix. I won't go into details at all. So first of all, we have a vector x1 and y1, and we said, suppose we want to move it to another vector. So how do we do it? So let's do a step back. You remember that the scalar product that introduces some slide before between two vectors. This is a way to assign to two vectors a number. Okay, and one can, you remember the rule is this one, and there is a pictorial way to represent this rule. If you allow me to draw the vector in this way, and in this way. This will be, this is, at the moment is just a trick, a visual trick to help with the realization of the scalar product. So what I'm saying is that if we place the vector, this vector here horizontally, and this vector here vertically, we can go and we can go row, and we call this row. It's a row and this is a column. We can multiply a row by a column by doing the trick that the first element is multiplied by the first element here, and the second element gets multiplied by the second element here, and they get summed together, as we know here, and they're put x1 x2 plus y1 y2. Okay, now you might say, okay, but you're just playing with your notations, you're making a mess, but but this is a nice way to this is, if you want, when we draw this line here, a connection between two vectors, and we know that this vector and this component here x2 can be associated with these two numbers here. Okay, one way to do it is exactly to think about another vector here, which we will call x3 y3. Now the order is a bit odd, and if you do this multiplication that I've done up there, so the first one with the first and the second with the second, we get this number here. Now how do we get this number down there? Well, if you think about it easy enough, you can think about another vector and do the same. The first one with the first one and the second one with the second one, and we put it down here. So if you want, if you have two vectors, and now we have to change numbering system, but I will be clearer in a second. Let's do it this way. Well, it sounds messy, but it's not too messy, I hope. Okay, so if we put two vectors in this way and we apply the rule that each vector multiplies the vertical vector, we have this new, we have a new vector which has these two numbers which are related to these four numbers in this object here. Okay, what I'm saying is that if we apply twice this rule here, we can associate four numbers. We can associate four numbers. Well, actually, we can associate a new vector, which is the one in yellow that I'm highlighting here. A new vector associated to the old vector, which is the one, it's a vertical one, by using four numbers. And guess what? What happens is that we can actually define, if I find my pen somewhere in the graph, I lost it again. Okay, we can associate, let's call it black. So in general, we can draw it this way. Let's pick square brackets and let's pick four number. Doesn't matter, well, it can be any four number that you like. And then we have our vector, which is x and y. If we now do the scalar product, let's say, of each row with the vector, okay, we take the rule that we know up here, we can create a new vector here, which is a plus a2, and then then a3 plus a4, and here is x and y, x and y. Okay, and as you can see, just by using those simple rules and these four numbers, we'll call it matrix M. This is a matrix M. We associated a new vector which called x1, y1, because there are still two numbers in a vertical column, to the old vector x and y. And this association is given by this matrix. So the matrix, if you like, is a nice way to transform a vector in another vector. Now, you cannot do, depending on those four numbers, and there is a bunch of beautiful math and algebra that you can dig into in matrices, but you are allowed to pretty much do any transformation that you think about a vector. But at the moment we are interested in just rotation. So let's see if we can guess what a rotation is, and then in future slides I will maybe do a better connection with rotation. But I want to jump to a little bit to the conclusion to not overdo with these videos on matrices and rotations. So the thing that I want to highlight is that this is not something that is related to two-dimension only. It can be, of course, generalized to n-dimension. You can enlarge the matrix as large as you want. The vector gets larger and larger. Then it's hard to visualize it in 3 is already hard to draw. In 4 it's very hard to think. More dimension is, I think it's impossible to visualize, in my opinion, but you can get tricks to help your head visualize this bigger matrix. But the trick is the same. So you have many components and as many number here, and then you twice as many number there, and then you do this multiplication. So where the rotation comes into play. Okay, so let's do one simple rotation. Let's do one simple rotation, and then I will do another simple rotation, and then I will lead you to the idea on how to create a general rotation. At least an intuitive idea. So let's start with the easiest rotation. Okay, so we have this matrix here. We set square and we keep square, otherwise I get confused. And if you think about the easiest rotation, which is the rotation that does nothing on your vector, so you have your vector, green, we like green vectors, and we want to keep it there. So the rotation alpha equal to 0. So what are the numbers? I will tell you the numbers. I'm not going to derive it because it's boring, but I will prove it that is correct. So the number that you need to put here, the 4 number, are 0, 0, and 1. This is called identity matrix. Identity because it's like the 1. It's like the 1 for numbers. If you multiply 1 times 2 is 2, 1 times pi is pi, 1 times a is a. So this is 1. This matrix does the same. The identity matrix, written like this, times any vector gives you the same vector. Okay, why this is the, so it's like the 1 in the matrices. And by the way, matrices are can also be thought as vectors. Not to confuse you, but just to let you know that the definition of the vector that I gave also apply to matrices, because you can multiply, so sum them, multiply by number, and there is also a scalar product, as we will see in future videos. But okay, let's stick with the idea that this is the right matrix that we want. Why is this the case? Because if we multiply this times this is 1 times x, and then the second one times the second one is 0 times times y, and then we do 0 times x plus 1 times y. Okay, now these two terms are 0, so they cancel out. These other two are 1s, so we know that 1 does nothing to the number. Therefore, we have checked that our vector stays the same. So this is the easiest rotation that you can think of. Now, let's do a bit more complicated but still easy rotation. And let's call these rotations, so I, the identity, we can call it rotation of the angle 0. And then we call our rotation, let's call it rotation 2, or actually let's call it rotation 45, because it's degrees. It's rotation of an angle of pi over 4. This is just a notation to address these 4 numbers. So this is rotation with angle 0, rotation with angle pi 4. So what is pi 4? We know already what pi 4 is. Pi over 4 is 45 degrees. And if you draw a line at 45 degrees, which is half of the 90 degree, we get a square. And if the length of the vector is 1, as we keep for the moment, the length is 1, not the length is 1. So the position, the coordinate, we know already that are 1 over square root of 2 and 1 over square root of 2. We know that because of Pythagoras. So we know that 1 over square root of 2 squared plus 1 over 2. We said it already, but it's nice to repeat it. This is 1 squared, which is 1. So we know that if we have a square, and this angle is pi over 4, because it's 45 degrees, pi over 2 is, pi is 100 degree, pi over 2 is 90 degree, and pi over 4 is 45. How do we write this matrix? So this matrix here, if I'm not wrong, hope I'm not doing it wrong, so let's do it for the vector 1, and let's see if it works. So I will give you so let's start with the vector that lies on the horizontal axis. So we start with the vector here, which is length 1, which is 1, 0. Okay, so the first vector, the first component, will be rotated by 45 degree, and we know that the component will be 1 over square root of 2 and 1 over square root of 2, positive. So these two numbers here will be, of course, 1 over square root of 2, and we don't know what it is here at the moment because there is a 0 here. So 1 times 1 over square root of 2, we get 1 over square root of 2. Okay, this is correct. Now, the first number is there, it's correct. If we move this component, how do we get this other component? Okay, we cannot use this number because this number will be multiplied by 0, so we will get 0. So let's see if we can use this number. No, because this number will be multiplied by the x component. So we need to use we can use this number here because it gets multiplied by 1, and this is 1 over square root of 2. So the first can be multiplied by the first, and we get another square root of 2. And this is already nice because if we multiply, it looks like we don't need the other two elements of the matrix. But we know that the matrix has 4 numbers and it needs to work for every vector. So this is just a bit of the matrix, and we use on purpose this easy vector to find the first two elements of the matrix. Let's use, this is correct by the way, this is whatever number we put here, this will be correct. So at the moment, let's cancel out this here, and let's pick another vector, which is, I'm choosing this vector on purpose. I will give you an idea what they are and maybe other slides, but let's call them this special vector, I call base vector, which defines the axis basically. So if we now consider this vector, which I draw up here as a vertical line in y, and we rotate it by 45 degrees in the same direction, we know that we will get another square, but this time this component here will be minus 1 over square root of 2, and this will be still 1 over square root of 2. So how do we do that? So this is easy, because so we multiply, the first will be 0, and the first component needs to be an x minus square root of 2. So this is minus 1 square root of 2, because this times this is 0, this times this is 1 over square root of 2. Now we know that the y component is still 1 over square root of 2 with a plus, so this will be 1 over square root of 2 with a plus, because this times this is 0, and this time this is 1 over square root of 2. Okay, so we found a matrix that, at least for these two vectors, accomplish a rotation of 45 degrees. What I claim, I'm not proving it, but I claim it's correct, that this matrix actually does a rotation of 45 degrees on any vector, which we will draw here, and x and y, and this will be x1, y1, and this will be rotated by 45 degrees. I'm not going to prove it, but believe me, it's correct, and maybe I will prove it in another video. But let's write this matrix here. Okay. Now I want to do another step, and then I will give you a general idea of. So you see that now we are looking at numbers that we saw with the sinus, right? Pi over 4 is 1 over square root of 2, one of the number in the sinus. 1 is associated to 0, which is one of the number associated in the sinus function and the cosinus as well. Now we do another one, which is r, we flip the vector. So r of 45, let's do 90 degree. Okay, rotation of 90 degree, so rotation of pi divided by 2. This is the angle, 90 degree or pi over 2. Okay, so what is the rotation of pi over 2? I can cancel this one. We understand the rule. Okay, this is x, and let's draw this. You know this is identity matrices. It's like the 1, the number 1, 0, 0, 1. Easy. This is rotation by 45 degrees. Rotation by 90 degree. Rotation by 90 degree, basically, it's very easy, because we just need to swap the x-axis with the y-axis. Okay, so my vector goes to, that is lying on the x-axis, will be of length 1. Okay, of length 1, and then it needs to be rotated by 90 degree. As you can see, this is 90 degree, and it will be y equals to 1. How do we do this? It's easy enough. So we take, as we did before, we do component by component. We take the first vector, which is actually the one we want to rotate 90 degree, and the result will be a 0 here, because this is a vertical vector, which is called 0, 1. So we need to get a 1 here. So this is a 0, and this is a this is a 1. Okay, sorry, we don't know that that's a 1. We know that this is a 0, and this is whatever number can be any number here at the moment, because any number times 0 is 0. So this is correct. The good thing is that this needs to be a 1. So if we multiply this by 1, we get a 1, and whatever we put here, it's fine, because it will be multiplied by 0, so we get 0. So I think we're done with the first two elements of the matrix. Now to fix the other two, as we did before, we consider the other special vector, 0, 1. And we know that this is a result, so this will be easy enough to find. This will be a 1, and this will be a 0. Because if we multiply now the full multiplication, we know that we see that this is what happens basically. 0 times 0 times 1, this is 1 here. And if we multiply the 1 times 0, 0 times 1, this is 0 times here. So this matrix actually moved the vertical to the horizontal and the horizontal to the vertical, which is correct, because if we rotate again by 90 degree, oops, this is a minus 1. This is minus 1. I forgot a minus, it's important. Minus 1. And therefore this is 0 times 0 times 0 times minus 1. Yes, I forgot the minus. This is important. Minus 1. Okay, so the minus was there as well in the rotation of 555 degrees, so it makes sense that it's there for the 90 degree as well. So no surprise, we are constructing these matrices with simple angles, but we keep referring to numbers that we saw in the sinus and cosinus, because if you remember the sinus and cosinus slides, we go from 1 to minus 1, and then when it's pi over 2 is pi over 4 is 1 square root of 2, and then if we circle back by other 290 degrees, we will get back to the identity. So in a sense, these rotations are periodic. In some, these matrices are periodic. In fact, if we take the rotation of what rotation? So pi, we can do pi, but it's okay. And then we do rotation of 2 pi will be the same as identity. So in a sense, the rotation are periodic as well, the matrices, in the same way that the sinus and cosinus are periodic. I'm not going to prove it now, but I will give you the result. And just to conclude these videos, is that the rotation, the general rotation in 2 dimensions with real numbers, rotation of alpha, is given by the cosinus of alpha minus sinus of alpha times sinus of alpha cosinus of alpha. Okay, and basically this fact here is quite important. I hope I didn't put minus, it should be fine. It's correct, yes. There should be a minus, maybe, yeah, no, it's correct. So, okay, this is not a very, so this is just an intuition that leads to the idea that the rotation are related to the sinus, but you see that it doesn't change the length of the vector, because this vector is equal to 1, and if we put any other length of the vector, it will not change the length of the vector. I want to tell you this to finish off, is because if you multiply this by a vector xy, for example, and we take the first component squared, we also know that we also know that cosinus square plus sinus square equals to 1. So this implies that the length of the vector will not change. Anyway, you can play with it with the rule that I gave you, and it will turn out to be true. So okay, so hopefully this is not too confusing. I will get back to matrices in other videos and try to give other examples. But what I want to hopefully to understand is that a matrix is a way to manipulate a vector, the component of a vector, such that you get another vector in the end with particular properties. Depending on the particular properties of these four numbers, there are many factors that can play into this game. The vector will have some properties as well, and then you can transform some in some others, and or not, depending on the properties. Okay, I hope it's clear, and I see you next time with more math and possibly at some point physics. Have a good day. Bye.